Hello, welcome to our talk on general purpose vision. My name is Tanmay Gupta. I'm a research scientist in the prior team at AI2. This is work done in collaboration with Amita Kamath and Ani Kemavi at AI2 and Professor Derek Hoem at UIUC. Today, computer vision consists of two kinds of models, single purpose and multi-purpose. An example of a single purpose model is an image classifier trained on the ImageNet dataset. Such a model is able to perform one and only one task really well, in this case, categorizing an image into one of 1,000 ImageNet categories. However, training a single purpose model, even on a new dataset for the same task, often requires an architecture change. For example, we may need to replace the last classification layer to match the set of categories in the new task. Models for monocular depth estimation are another example of single purpose models. They are designed and trained for the sole purpose of predicting depth from a single image. On the other hand, we have multitask models such as mask-CNN, which can do detection, instance segmentation, and pose key point estimation simultaneously. While such models handle more than one task, they are still limited to a predefined set of tasks. The architecture and learning algorithm design are heavily tailored to these pre-selected tasks. In vision language models, for example, this pre-selection of tasks manifests itself in the model design in the form of multiple task-specific output heads. In some cases, even different data sets for the same task, like the VQA and GQA dataset for the visual question answering task, may have dedicated output heads to support different answer distributions. In short, the story of computer vision so far has been one of n-purpose models. N equals 1 for single-purpose models, and n greater than 1, but still pre-selected and small prior to model and learning algorithm design for multi-purpose models. This makes it difficult to scale systems built for n tasks to m new tasks. Often, even adding one new task requires non-trivial modifications to the network architecture or the training process. Our goal is to make a leap from n-purpose models to general-purpose models. In contrast to n-purpose models, for general-purpose models, n is large and unknown at design time. In other words, in case of n-purpose models, the system is expected to only be applied in predefined scenarios, whereas for general-purpose models, the system is expected to encounter and adapt to new tasks within a broad domain. Any discussion of general-purpose models would be incomplete without a discussion of foundation models. Recently, the term foundation models has been used to describe any model that is trained on broad data at scale and that can be adapted to a wide range of downstream tasks. Current generation of foundation models includes models such as CLIP, DALI, BERT, and GPT-3, which not only demonstrate impressive generalization performance to new data distributions, but also surprising emergent properties, such as GPT-3's few-shot learning capabilities. Let us put a pin on this and we'll get back to the relation between foundation models and general-purpose models towards the end of this talk. Now that we understand the motivation behind general-purpose vision systems, or GPVs, it is time to define a set of guiding principles for building such systems and measuring progress towards this grand goal. Here, we have defined three tenets of GPVs, namely generality of architecture, generality of concepts across skills, and generality of learning. Let us look at them one by one. The first tenet is generality of architecture, which says that a general-purpose architecture should be able to support a wide range of tasks within a broad domain without requiring any change to the architecture or learning algorithm. Here, we draw inspiration from biological general-purpose systems. For instance, us humans have very limited number of inputs, namely the five senses, sight, smell, taste, hearing, and touch, and very few outputs, our limbs for locomotion and manipulation of our environment, and the ability to synthesize sound. Somehow, we still manage to accomplish an astonishing range of tasks in this world. Note that we do not need to sprout a new head or limb in order to learn new tasks. Even organisms like octopus and lizards, which can regenerate body parts, do not keep adding limbs during their lifetime. In the digital world of AI, this has also been shown to be possible in the domain of NLP, where fairly general-purpose encoder-decoder architectures have been successfully applied to a wide range of tasks. There is also a growing body of literature in NLP on learning from task descriptions, which further blurs the task boundaries. These task descriptions range from templated to complete natural language descriptions. Learning from task descriptions offers several attractive properties. Task descriptions can simplify a large number of NLP tasks to encoding and decoding a sequence of text tokens. In turn, this allows the model architecture to be task-agnostic as long as it supports encoding and decoding of text tokens. Finally, task descriptions offer the possibility of zero-shot task generalization, that is, the ability to solve new tasks described in natural language that the model was not trained on. So here's what one potential solution for GPV could look like. We could let the tasks be specified through natural language prompts, and we could equip our model with a small number of modality-specific output heads that are reused across tasks. For instance, if a model is equipped with only 4 output heads for producing text, bounding boxes, region relevance scores, and images, the model could be trained on a diverse set of tasks. Classification labels could be predicted by the text head. VQA and captioning could use the text head for predicting answers and captions, and box and relevance heads for predicting interpretable attention maps on the images. Box and relevance heads could also be used for object localization and refragging expression comprehension. And finally, the image head could be used for tasks such as depth prediction, semantic segmentation, instance segmentation, and image-to-image translation. In this work, our first attempt at creating a general-purpose vision system focuses on the highlighted output heads. This is what the architecture of GPV1 looks like. At a high level, GPV1 has encoders for vision and language inputs, and decoders for boxes, region relevance scores, and text. The vision encoder consists of a CNN backbone and the transformer encoder and decoder from DETER, a transformer-based object detection model that replaces hand-coded anchor boxes with learned object queries. We use pre-trained BERT as the language encoder to encode the task description. The vision and language encodings are fed through Wilbert's co-attention module for cross-modal contextualization. The resulting image region and language representations are used to decode various outputs. A transformer decoder is used to decode text outputs such as captions, answers, and category names. And a vision decoder is used to decode boxes and relevance scores. The box head outputs region proposals independent of the task description using image features from the DETER decoder. The objectness head produces task-agnostic objectness scores for each region. The objectness scores are then combined with task condition relatedness scores predicted by the relatedness head to obtain the final relevance scores. Details and ablations for other architecture components, such as ROI pooling in the vision encoder and relevance conditioning in the cross-modal module, can be found in the paper. A general-purpose architecture needs a general-purpose learning algorithm. GPV1 is trained jointly on 4 tasks: localization, categorization, VQA, and captioning. Each mini-batch contains a mix of random samples from all 4 tasks. We initialize the vision encoder and decoder with weights from pre-trained DETER and fine-tune all components except BERT to reduce GPU memory footprint. The model is trained using only 2 losses. Samples that provide bounding box supervision, such as those from the localization task, are used to compute DETER's Hungarian loss. And samples that provide text supervision, such as in the case of categorization, VQA, and captioning, are used to compute the negative log likelihood of the ground truth text. Both these losses are minimized via the AdamW optimizer. Here are some examples of task descriptions and respective outputs produced by GPV1. Irrespective of the task, the model always produces text, bounding boxes, and relevance scores. For instance, the model learns to identify relevant regions for VQA and captioning and generates informative text for localization task without receiving supervision for those modalities in context of the respective tasks. We also provide an interactive demo and plenty of randomly sampled qualitative results for you to understand GPV1's capabilities and limitations. The second tenet of GPV is generality of concepts across skills, which says that a general-purpose architecture should be able to perform tasks in novel skill-concept combinations. To understand the second tenet, we need to understand the idea of skill-concept factorization. Let's say a model does well on answering visual questions about dogs. We can then say that the model has learned the skill of VQA for the concept dog. Similarly, If a model is able to localize cats, we could say that the model has learned the skill of localization for the concept cat. The principle of generalization of concepts across skills says that a general purpose model that has been trained to localize cats and answer questions about dogs should now be able to answer questions about cats without being trained on VQA data for cats. In other words, the concept of cat learned in the context of localization should generalize to other skills. Similarly, the model should be able to localize dogs without ever receiving bounding box supervision for dogs. In this case, the concept of dog learned for the skill of VQA is expected to generalize for the skill of localization. To evaluate skill concept generalization, we have created the COCO-SCE dataset, a new split of COCO that explicitly tests for performance separately for both seen and novel skill concept combinations across 4 skills and 80 concepts. Specifically, we split the 80 COCO categories into 3 subsets. The first subset is held out from the VQA and captioning training data. The second subset is held out from classification and localization training data. And the third subset consists of categories that may be seen in context of any of the 4 skills. Note that the concepts held out from VQA and captioning have the opportunity to be seen in classification and localization tasks, and vice versa. We use COCO-SCE to evaluate skill concept generalization of GPV1. For each task, we report the performance on the full COCO-SCE test set, performance on the subset of the COCO-SCE test set containing no held out category, as well as performance on the subset that mentions any of the unseen categories in the task description or the output text. To establish a baseline, we retrained single-purpose state-of-the-art models for various tasks on the respective COCO-SCE training data. We do not use Anderson et al.'s popular visual genome trained bottom-up top-down features for any of these tasks, since that might expose unseen concepts and therefore invalidate the conclusions from the study. Instead, we retrain faster RCNN using box supervision from COCO-SCE train set to provide region proposals and features for these baselines. First, we see that GPV1, when trained on individual tasks, is as competent as the state-of-the-art models trained on the same data. However, when trained jointly on 4 tasks, GPV1 shows significant gains over single task GPV1, especially on unseen skill concept combinations. Significant gap still remains between performance on unseen concepts for each task. Finally, we establish an oracle upper bound on unseen performance by training on the original COCO train set that lets the model see the skill concept combinations that were held out from COCO-SCE train set. The third tenet of GPV has to do with generality of learning. A general-purpose architecture should be able to learn new tasks with minimal loss of performance on previously learned tasks. There are 2 core challenges to this third and final tenet of GPV. The first challenge is achieving high sample efficiency for new tasks, and the second challenge is retaining what has previously been learned when learning new tasks. We analyzed GPV1 trained on 4 tasks with respect to both of these challenges by learning a 5th task, that is referring expression comprehension. To begin with, we observed that GPV1 already achieves reasonable zero-shot performance on the referring expressions task, and that the multitask model significantly outperforms GPV1 trained only on the localization task. We do observe errors in the zero-shot setting due to the model being unable to distinguish between instances based on the attributes used in the input referring expression. However, many of these errors are corrected once we start fine-tuning the model on the referring expressions training data. Here, we plot performance on the referring expression task versus the amount of referring expression training data used. We observe that multitask GPV1 is more sample efficient when learning this new task when compared to GPV1 trained only on the localization task. We also measure percentage of the performance retained on the previously learned tasks as we train on increasing amounts of referring expression training data. While multitask training does not eliminate forgetting, it does seem to improve retention when fine-tuning on new tasks in comparison to a model trained only on a single task. Now that we have a better understanding of GPVs, the three tenets, and the evaluation methodology, let us go back to our discussion of foundation models. In spite of impressive generalization performance achieved by foundation vision models like CLIP and DALI, their contributions in some sense have been in scaling the number of concepts for specific skills, namely image text matching for CLIP and text to image generation for DALI. However, scaling the number of skill concept combinations while satisfying the three tenets of GPV continues to present an exciting challenge for the vision community. In the short term, various foundation models may provide useful representations or capabilities as building blocks for general purpose systems. But ultimately, we hope to see increasingly capable general purpose vision systems lay the foundation for vision and AI research in the coming years. Being the first step towards general purpose vision, GPV-1 has several limitations. Due to a lack of image generation head, it does not support image generation or manipulation tasks. There is no explicit mechanism for handling forgetting. The model is difficult to train from scratch and needs to be initialized with pre-trained DETR weights. And the compute requirements, while nowhere near some of the large-scale foundation models, are still quite high. Here are some quick takeaways. Vision models today are end-purpose models. We believe that recent advances in vision and NLP research provide a strong foundation to start tackling the problem of general-purpose vision. We laid out the three tenets of GPV to serve as guiding principles in the pursuit of GPVs. And we built and analyzed GPV-1, a task-agnostic vision language architecture, as a step towards general-purpose vision systems. Check out the web demo, randomly sampled qualitative results, and code for GPV-1 at these links, and thanks for your attention.